question?
Actually, hold on one second. I'm gonna go live on YouTube right now. So, hello, welcome everybody. And before you answer the question, let me actually set you up. Let me introduce you. So, all right, cool. We are now live on YouTube. Welcome everybody. Thank you so much for being here. We are really excited for this workshop. We have Brecht, hopefully I'm pronouncing that right, from Loopring team. He's the chief architect. To go over, zkRollups and anything else he wants to go over from the Loopring platform. We're really excited to have them. Again, these guys also have a bounty for using their projects. I believe it's 3, each at 1,200, I think. You can check the dev post to verify. But yeah, really excited that this is a really powerful tool. So with that, I will pass it over to you. Thank you so much for being here.
Okay. Thank you, Patrick. Okay, let's start with, there was already a question for like an in-depth question about zkRollups, but let me first, let's see. Share my desktop. Okay.
Yep,
let me first start with like a small overview of what Loopring is and how we are like the main goal of the bounty is building an AMM on zkRollups on our new Loopring 3.6 release. So let me first give a small overview of what Loopring 3.6 is and how we can extend like some basic functionality inside Loopring 3.6 to build like richer functionality, so things like AMMs. So yeah, let's start with the overview with like what zkRollups are, so everybody kind of has an idea of what we are trying to do, what the specific problems are, and how we solve them. So let me first switch to the design doc, which has this Merkle tree format. So what we do is we batch a lot of transactions inside a block, very similar to like a normal blockchain. And all the transactions we do in the block work on this Merkle tree. So if you do a transfer, then you just move one balance over to another account, and you approve that just like in a normal way. You sign a transaction like you normally would, and we update these variables using logic that's specifically written for zero-knowledge proofs. So we have like this fixed logic, which makes it possible to generate proofs on top of them. But I'll get back to that later. So all the state that we change is store and actually use is stored in this Merkle tree. So I have this other image here that I found on the internet. Is like how this actually works is so like basically it's like I said, it's a blockchain. There are a couple of blocks. A block contains a number of transactions, and these transactions change one Merkle tree state to the other one, and these transactions they work on the Merkle tree exactly, and these transactions are proven with a zero-knowledge proof. And so every time we submit new work on chain, we have to batch all these transactions together. This is done by the operator. The operator batches these transactions together and generates a very small proof for them. So that's what provides us with like the security and scalability. We have like all this data, all this transaction data, all these signatures which need to be used to verify if the user has signed the transaction. We have also all these balances that are stored in the Merkle tree. Trading history is stored in the Merkle tree. All of that is stored in the Merkle tree. But on chain, we just submit like this single Merkle root and this single proof, which makes sure that all these transactions will validly execute in a valid way. So they are proven to be correctly, even if we don't execute them directly on chain, which is like a very nice property to have. And it's as secure as Ethereum because all these transactions, we also post some data for them on chain. So one of the problems, like this is the data availability problem. So all this state is stored in this Merkle tree. Only this Merkle root is posted on chain. But to generate proofs for our system, so like for zkRollup, you actually have to have all the state available because you have to have like this Merkle proof. So you have to show that you know that some kind of data is available in the tree. So to be able to generate the proof, you need all this data. So zkRollups solve that by, for all these transactions that were executed, you also post like the resulting Merkle tree deltas on chain. So everybody can just recreate the Merkle tree just by looking at what's happening on Ethereum. So if we wouldn't do that, then we are still sure that all the transactions were correctly executed because we have this zero knowledge proof, but you don't really see what's happening on chain. So there could be like a transfer that's executed, but you don't really know that that transaction was included in a block because you can't see what's happening. So this posting of the data solves this problem. And if you post the data, then it's called the zkRollup. If you don't post the data, then you kind of expect there to be some kind of third party or multiple parties that provides this data to users. So you can still see what's going on, but that's less secure because then you have to trust those external data providers. So that's called Validium or zk Plasma or some similar names. There's a lot of names for that. So, but if you post the data on chain and you have this zero knowledge proof, then it's a zero knowledge zkRollup. Okay, so I hope that's kind of like a short overview of what zkRollups are. And yeah, this is one basic version we've been online with starting this year, but with 3.6, there are a lot of improvements that we have done, which are very important for like especially for the EMMs, but also very important for like extending the functionality that we can do. So if we switch to the design doc quickly, so there's only a couple of transactions that we support directly in the zkRollup. So we have trades, which is now limit trades, limit orders, and AMMs, just the swap logic for AMMs. We also have transfers, deposit, withdrawals, account updates to set zkRollup specific public keys, because we have like special signature types that are very efficient on layer 2. We also have that Emm update, which I'll talk later more about. But that's it. So that's kind of the basic functionality that's completely done on layer 2. And now we are, well, the goal of the bounty is that we use this basic functionality, which is very efficient, to like make this like more richer functionality. But first, I'll talk a bit more about 3.6 and how 3.6 actually is needed to do all this stuff, because our current version 3.1 is well, it's much less flexible in that way, and I'll use this presentation to show why that is. So this is a presentation that shows the differences between 3.1 and 3.6, and I'll elaborate on how this helps us to build like more interesting features on top of that basic functionality. So first big change is like currently there's like a high gas cost to get users on board, because every user has to do an Ethereum transaction to make an account on the zkRollup. This was well, this was fine if gas prices are low, but now it's getting more like it's a big problem because gas prices are so high, and so getting on board on the zkRollup is very expensive on 3.1. So on 3.6 we fixed that by well, by two things. So people don't have to explicitly onboard anymore to receive funds from other users. So that's basically as cheap as a normal transfer. But also users that want to create an account don't have to do an Ethereum transaction anymore. They just have to sign that they want to create an account, and then we use that signature on-chain to still cheaply set up their accounts with their own public keys. So it's only like around 5,000 gas to completely set up a user inside the zkRollup. We also increased like the capacity of a lot of stuff in our Merkle tree, because this Merkle tree I've shown before. It's like well, it's important because that's where we need to store all of what we use inside the zkRollup. So we used to have just 1 million users and like 250 tokens. But now we have increased the capacity to like, we now have like 32-bit accounts. So like more than 4 billion users, more than 4 billion accounts so that can be used. And we also use 16 bits for the tokens. So we can have like, this is well, a bit outdated because now we can like have more than 65,000 different tokens. So we have some limited support to even support things like non-fungible tokens, NFTs, as long as they don't need to have too much unique IDs. So we also do like this a custom deposit contract. So we store user funds in this external contract that exchanges can write themselves. And this external contract can provide extra functionality on top of like the basics ones that are built into the protocol. So those funds used, deposited by the users can be used like in a productive ways, but you can also implement new token standards and flash loans and like lots of interesting stuff there as well. So yeah, for like there's now like lots of ways to authorize transactions. So you can authorize transactions, like most of the transactions you can authorize like with the zkRollup specific signatures, which are very efficient. You can also authorize them with like standard Ethereum signed messages, which are still pretty efficient, but like the benefit is that you don't even have to have this zkRollup specific public keys. You can just write authorize transactions with your normal Ethereum addresses. So that's another benefit. And you can also authorize transactions like with an Ethereum transaction. So you can authorize, like this is useful for contracts. Yeah, basically for contracts, but these contracts can also be like general purpose functionality built on top of the exchange. So we call those agents. So if you have like we built, you can have like some additional logic inside a contract. And like, let's say for this contract, just verifies if a user wants to do a transfer, checks the signature, and then this contract can authorize a transfer for that user using whatever on-chain logic that's needed. So that's also one of the things that we'll use for the EMMs. So this EMM pool contract can authorize transactions for a specific user, and this user can authorize this contract to do that or not. It's kind of like similar to like how you approve spending by a contract for an ERC20 token. Now you can authorize a contract to authorize these transactions for you. So that's kind of like one of the important things that we've added and that we actually already use in like multiple ways. So we have like these fast withdrawals, which work on top of that, and now these EMM pools as well. So that's kind of yeah, an important feature. So 3.6 also introduces like universal blocks. So in 3.1, we kind of like optimized everything as much as possible because well, zero knowledge proof generation was very expensive, and we didn't really know too much about how it would actually be used. So we tried to reduce costs as much as possible, and we had less like these different circuits for every transaction type, which makes, in theory, that makes things less expensive, but it also makes things more complicated, and depending on how many transactions we actually have to do, it can actually make things more expensive, because if you don't have enough transactions to fill up a complete block, then that's a problem, because the bigger the blocks we can commit on chain, the lower the cost will be, even if like there's some extra costs because the universal block is like bigger and more expensive to generate the proof with. It's kind of still be in practice much less like a big improvement in cost, because we can just put all the different transaction size inside a single block and just do submit the single block on chain verification for all these blocks, so we can even verify the proof like in a very efficient manner. It's also like I said, like it's also pretty important because it just makes things a lot more easier to do, because we can just put all the different transactions after each other instead of like having to put transactions in the correct block, and then there could be dependencies between those blocks, and it just makes the life of the operator much more difficult to keep track of all that stuff. 6, because we have now this universal blocks, we can also just add dummy blocks, the dummy transactions to pad a block. So we don't really have to like add actual dummy transactions that don't have state changes directly, but now they are nicely like no operations, which are all zero data on chain. So it's also a bit more cheaply. So yeah, fast withdrawals, not important for now, but yeah, it's building on top of the agent functionality. Receipts also like one of the things that we use the data availability data for. So because we have like because we have posted all this data for these transactions in the block, it's not only useful for like solving the data availability problem. Because we have the data on chain, we can also use this data to read it on layer 1 and then use it in interesting ways. So that's one of the things we always will also use for the Emm pools. So this data is on chain, and we will verify if these transactions that were included in the block were actually the ones that we expected to be included in the block, with whatever on-chain logic that we need. So yeah, the more flexible authorization, I think I already said. So lots of ways to actually do transactions, authorize transactions for users in the rollup. Also a couple of like trading stuff. So specific takers for orders. Also like a special way for transfers to be authenticated. So you can there's a way to set up transfers that need to be signed by 2 keys instead of just the one stored in the account, which can be used in like a couple of interesting ways. Also like the 212, so like depositing and withdrawing. It's kind of like you can go from layer 1 to layer 2 in any direction, in any way you want. So from layer 2 to whatever layer address on layer 1, and from any address on layer 1 to any address on layer 2. So pretty flexible there as well. Okay, so I think that's kind of like the short overview of 3.6. So I guess lots of the things to think about, but now to make it a bit more concrete, I'll start explaining more about how we built the Emm pool on top of that functionality that you just saw. But first, I'll first explain like what we built in for the EMMs inside the protocol. So you know what's possible there. So yeah, and then I'll check if there are any questions. So I don't go too fast or too slow. So what we built inside the protocol is like the balancer formula. So this is the curve paper, which kind of has like a nice introduction about the different curves that we can follow. So this one is the there's the Uni Swap Formula. So just no, that's not the one. So it's kind of this is the Uni Swap Formula. So it's like just x times y is some constant, and this constant is kind of like, you can implicitly derive it from the current balances inside the account. So this is quite kind of like very, very elegant formula, because you don't really have to store any data for it. You just have the balances, and then you can you basically have defined the curve already. But the one the swap logic, like the swap logic that we use inside the circuit to do efficient swaps, is the balancer one. So it's the balance times to the power of some weight, and then the product of all these different tokens in the pools is also some kind of constant, which is nice to have, because there's like this single parameter that this depends on. So this is one parameter that you can set inside the Emm pool, or like you can have we have a zkRollup transactions to set this weight, and then once you've enabled this weight, then this kind of like automatically enables for the account. So it's kind of like a very elegant way. And also the swap formula only depends on like the ratio of the weights between those two tokens. So even though that there's like there can be multiple tokens inside the pool, like more than two, the swap logic is still very simple, because it doesn't care about what the other weights are of the different tokens. Like 10 tokens in the pool, it doesn't matter what the other 8 weights are of the other 8 tokens. It only depends on like the 2 tokens you are actually trading. So that's kind of like kind of important to have, because otherwise it would greatly complicate the swap logic we have to do, because we kind of don't have the circuits, like the logic that we need to implement in the circuits is kind of like fixed, and you can't do dynamic loops or anything like that. So this way we just have to depend on 2 tokens in all cases, and it's kind of like nicely works out. So I'll have to jump here to the actual Emm Update transaction. So this is the transaction you can use to update the weights, like update the weights inside the Merkle tree, and also like enable Emm trades for that account. So if you set the Emm weight to a non-zero value, then implicitly you also enabled Emm for that token. So if you have 2 tokens that have a non-zero token weight, then the operator can create orders for that account, as long as the resulting state of doing the trade matches the balancer curve. So instead of like defining some other order type or whatever, however you can enable it, it's just we basically generate standard limit orders for the Amm account, and the only thing that we have to check extra is if this balancer curve is still valid. So in that way, it's kind of like very elegantly integrated into our trading circuit, because everything remains the same. We just have this like this single extra check if this remains valid. So yeah. Okay, let me see if there's any questions. Okay, yeah. So the first question was for privacy on the zkRollup level. So our zkRollup doesn't have any privacy, because yeah, we have to publish all the deltas on chain for the data availability problem. To solve that, you have to anonymize that data as well. So you have to publish like these extra hashes, like you have to publish hashes on chain, which you can then fill the Merkle tree with. And you also kind of need like recursive snarks, because yeah, you kind of have to validate a zkRollup, zk proof inside a zk proof. So that's kind of like pretty expensive now, but like yeah, people are making a lot of progress there. So there's like a Aztec that will have this zk rollup type of transactions. which will still be more expensive because the amount of data that you have to put on chain will be larger. So now we can have like this compressed amount of data. So if you transfer, if you do a simple transfer, then we can check here the design doc. So here is the list of the actual data that we push on chain for this transfer. And as you can see, like it's very it's done in like a very compressed way. So instead of posting Ethereum addresses, we only post like short IDs. Instead of doing token addresses, also just a short ID. The actual amount, instead of using a simple 32 uint, we compress it to like a decimal float to 3 bytes. Fee payments as well, just 2 bytes for the token and 2 bytes for the actual amount. So all this stuff is very compressed. So we can do like all the things that we need is just 20 bytes. And we know exactly what happened in the Merkle tree. If you have like additional privacy on that, then there's some extra overhead for that. So especially with these high gas costs, all the data that you push on chain just makes things a lot more expensive. Because even though like call data, you only post it in call data, and it's pretty inexpensive, like 16 bytes for a non-zero byte value. It still adds up because it's your main cost to that you get on chain. So it also reduces scalability and like pretty greatly increases costs. So hopefully things progress, like Ethereum 2.0 will have more data available. zk knowledge proofs are getting better. So recursive snarks will be pretty common. So I think we'll be seeing more of that pretty soon. So prediction markets. So does this support prediction markets is a question. So yeah, it does support it, but only if you like tokenize it. So if you can get the token in the exchange, then yeah, so then it's just like a simple transfer of that token or a simple swap of that token. But otherwise, like we are fixed to this like specific functionality inside the rollup, and if you want this richer functionality on top of it, then you still need to do some more stuff on chain. So we can't go too wild yet in the rollup. And for the rest, yeah, I'll make sure that everything I've used in this presentation I'll list somewhere so you can check it later if you want to. Okay, so I think that's all the questions. So let's jump into the actual AMM implementation. So I've because it's kind of like pretty specific how you would implement it. I've written this demo implementation, which already does quite a lot. So you don't have to worry about all this Loopring and zkRollup specific functionality. Okay, so first things first. So I said like how we can like extend the functionality of the zkRollup in interesting ways. So how we do that is to do extra callbacks on top of the block. So if we have a block that does a couple of transactions, we verify if those transactions are valid. So let me try to paint this so it's kind of like let's hope this works. So if we have like this block, this large block, and this block contains 3 transactions. So one of the things that we have to be able to support for AMM pools is like depositing multiple tokens. So we can and these tokens need to be supported like in one group, because if this pool has 3 tokens, then a user wants to deposit these 3 tokens inside the pool contract, and then he mints like some kind of liquidity token. So we have to, because we have to make sure that the Amm pool is like an honest way, so people can just cheat in some way to get more or less liquidity tokens, depending on how a user deposited funds on the Amm pool. We need to make sure that these 3 transactions which do the deposits are actually done in a group, and we can accurately calculate how many liquidity tokens the user gets for this deposit, for this join in the pool. So inside the protocol, we don't have any like a way to force this link between the transactions, and also inside the protocol, we don't have any way to do this minting logic. So this is quite specific for the Amm, like the type of Amm that we want to support. If you just want to support like simple Uni Swap or balancer pool, or like one of these new ones that are coming out, maybe that use price oracles, or even this stable credit that's coming out now. So this is kind of like pretty much like we don't want to bake it too much into the protocol, because things are changing rapidly inside these EMMs. So this logic, we want to enforce this logic in a smart contract, because it's much easier for people to write smart contracts on top of the basic protocol, instead of like having to write these zero knowledge circuits, which are very hard to write. And yeah, it's also much like people can write smart contracts, but not a lot of people can write circuits. So the way that's done then in the Amm pool is we check if all these transactions are done in this sequence. So there's like this callback. We check, okay, this is the pool contract, and this pool contract we check, okay, this user has deposited this much, the user has deposited this much, the user has deposited this much. Okay, now I know I have verified this, and now I will mint these liquidity tokens, and then I will make sure that this block that was submitted is actually also submitted on the exchange contract. So it's kind of like an atomic operation. The operator submits this block on chain. We have this additional constraints that are applied on top of this block, and then this block is like immediately as well is submitted on the exchange contract. It's verified and it's final. So we don't have any reverts that are possible, which is kind of nice to have and important to do this kind of functionality, because if you have reverts, then everything just gets a lot more complicated, because in our current version, you can first commit a block and then later prove it. But then you have all this logic that you may have done on layer 1, but then you have to revert. So it's just much harder. So by having this atomic operation that's possible, the block submission, direct verification of the proof, and the state is final, we also know that these liquidity tokens can be minted without the block actually being valid and everything being correct. So one of the interesting things here as well is that the Amm pool also has to authorize some transactions, and some of that can also depend on the state. So like let's say there's another, like most of the times it's like let's add it to the end, but this is like the an Emm update event. So the pool wants to authorize like a weight change or whatever. So this transaction of the pool, this transaction isn't yet authorized on the exchange contract. So before, when the operator is creating this block, this transaction hasn't yet been authorized. But because these extra constraints are need to be validated inside this pool contract, we run over these transactions, and then when we see that all things are valid, then we authorize this transaction as well. So this uses like the new agent functionality of 3.6. So we authorize this transaction by sending like a transaction hash to the exchange contract. So this is like, okay, this goes to the exchange. And this can now, everything is valid. This kind of like, okay, you can do this transaction. And once this callback has exited, so like, okay, now this block is valid for the AMM pool contract, then we actually submit it to the exchange as well. So and then this exchange contract checks for this transaction, like, okay, was this transaction validated? And because we've just validated it, like authorized it, now the block can actually be submitted. So this is also forces the operator to do these checks in the pool contract, because if this transaction would already be authorized in some other manner, then the operator could just not call all this enforcement logic and just do these transfers to the AMM pool, and like nobody would see what's going on, and users would just deposit to the AMM pool, but they wouldn't have their minted liquidity tokens. So that's basically how how this richer functionality is implemented on the basic functionality inside the rollup. So you can even say like these, like the where is it? Like these simple transactions type that you support. You could even call them like zk precompiles. So look, like you have some precompiles that you can use on Solidity. That kind of makes things much more cheaply than if you would have to implement all that stuff directly yourself in Solidity. There's like these precompiles that make certain operations much cheaper than they would be otherwise. So you could say that these transactions that we support in the zkRollup are kind of have the same purpose. So if you can use them like a precompile, then you can like have a lot of gains, because even if we wouldn't support spot trades directly inside the circuit, you can still emulate them with just normal transfers inside an agent contract. And so the agent contract would just verify the orders of the users and then do basic transfers between those users to do a trade. The benefit, of course, of doing it completely inside the rollup is that it's you can still do it much more efficiently, because you don't have to use layer 1 at all. But the benefit of doing it in an agent contract is it's a lot more flexible. So people can just write whatever logic they want in smart contracts, like they are used to, and then they use these zk precompiles to optimize it in the significant ways, because even though there's like these general operations are pretty specific, you can still use them very generally, because things like replay protection or fee payments and like all the storage you would always have to load and store on chain, all of that you can depend on the layer 2 stuff to do that for you. So that's kind of like very nice to have. So most times just making everything stateless is already a big gain, because most costs are like storage costs, and yeah, if you use this model, then everything is stateless. You just have to post the data on chain that you need, verify it, and then depend on the layer 2 to actually store everything that you'll need in the future. Okay, let's see if there are any questions. Okay, no. So I'll now go over the code a bit. Oh, somebody raised their hand. Is there a question? I'll wait a bit.
Mark, if you got a question, if you could type it into the questions chat, that would be great.
Yeah, probably we will be open sourcing our relayer. Well, not completely. So we'll probably open source like a very light version for only transfers, but like the complex stuff, the very complex stuff, like the order matching, we'll probably keep closed source for now. Okay, so I'll start running over some of the codes where you can add some functionality. So this is yeah. So to start at the beginning, like this is the place where blocks are submitted, and like this is where the block finally goes through the exchange contract. So this is where this additional constraints of the transactions goes on. So some callbacks can be specified here as well, and these callbacks are just called. So they just take up they just say like, okay, contract, look at this block at this transaction, and there's some extra data like auxiliary data that can be used to do that, and that's exactly what currently the AMM pool does. So this is like this callback that's called on the AMM pool. So you already this block, the transaction ID, and the transaction index, and auxiliary data. So the first thing we do is like this check. So this callback can only be called by the exchange owner. So we have to make sure that like not everybody can just call this function, because otherwise like some state changes can be done on this contract as well, and you can lie about which blocks will actually be submitted. So if you would be able to submit fake blocks here, then you can yeah, then this would not work correctly. So the auxiliary data here is just a list of all the pool transactions that need to be executed. So a pool transaction is just a join and an exit of the pool, and a join and an exit is just a grouped together deposits to this AMM pool, and a grouped exit is just token transfers from the pool to the user's account. And there's two ways that you can do it now in this demo version. So you can deposit from layer 1 or layer 2, and you can also exit to layer 1 or layer 2. So what this does is like these funds of the AMM pool are stored in the account on layer 2 of the. Okay, is there a question? Otherwise, I'll wait for the question. Not immediately, so I'll I'll continue for now. So yeah, so the pool, the funds of the pool need to be on layer 2, because otherwise, yeah, we wouldn't have any scalability benefits. So people can just trade on layer 2 like they would like with limit orders. So if people deposit on layer 1 to this pool contract, then eventually we'll also have to deposit like the funds stored in this contract to layer 2 as well. The other option is that users already have their funds on layer 2, and so the only thing they have to do is transfer their funds from their layer 2 account to the AMM pool's layer 2 account on layer 2 as well. So both options are available here, and yeah. So yeah, first we just check if like all the data is as we expect it to. Like there's some extra utility functions on the block, so you can easily read the block header and like all the transactions as well. So like in this case, like we have to let me go to the join. Like if the join is like yeah, so if the join is a transfer, then we read the transfer here on the specific transaction index in the block, and then we verify some data, and then we mint the tokens. But I'll get back to that later. So yeah, the first thing we have to do is an Amm update, because on layer 1 we don't really know much about the Amm pool. So to mint and burn the correct number of liquidity tokens, we have to know the balances of the Amm account on layer 2. And we don't have the data available directly on layer 1. So the first thing we have to do is pull the balances from the Amm account from layer 2 to layer 1. And for that, we can use the Amm account update. So Amm updates. So one thing this does is it not only is able to set the token weight of the token, it's also able to set like the fee that's expected, but that's it's not very important. But the important thing here is that it also pulls the balance from layer 2 to layer 1 in the data availability data, so we can read it on layer 1 at that specific time. So by doing layer 1, by doing this Amm update first, we know exactly what the balance in the account is, and we can use it to make sure everything works correctly. So I'll just jump to this process Amm updates function. So this is just what's happening here. So for every token, for all the tokens in the pool, we read the Amm update, so we know what the balance is. So that's written here. So we read the data from the block, and here's the balance, and then we store the balance locally, so we can work on it for processing all the joins and exits. So you don't have to do to get it on from layer 2 to layer 1 every time. We just keep a cached copy here, and we work on these balances for the next transactions. And here is also where we actually approve the transaction, because the operator included this Amm update transaction, but we don't want, of course, we don't want the operator to be able to actually authorize transactions for this pool account. So this transaction is only authorized when this callback is actually executed. So we know, so like what I explained, like on this diagram. So where is it? So yeah, this is like, okay, this transaction was included, but now this callback is called, which verifies these transactions. And then, okay, I've seen it, they are as expected. And then this authorization is done to the exchange. And this is exactly what's happening here. So this is this authorization through the exchange contract. So this Amm update transaction is actually valid and can be included in the block. Otherwise, if you don't do this authorization, then this Amm update would be invalid because it wouldn't be authorized. Okay, so this is like the start. At this point, we know what the balances are on layer 2. We've set the weights, we've set the fee that's expected, and now we will process all the actual operations that we need to do. So the joins and the exits. So let's go to the joins. Okay, so the join. So there's currently 2 ways to authorize this join by a user. So the user can submit like an approval on chain, and then it gets added to this queue. So if it's done that way, then we expect the funds to come from layer 1 currently in this demo application. Otherwise, the user can just sign a message, and then we verify if the user wants to join. So if no signature, if a signature is provided, we verify if the user actually wants to join, and then later we will actually approve this transfer from the user to the pool account. So it's kind of like a similar way. So the user only authorizes this join at this point. And again, because this callback needs to be called for this join to be valid and all the data of this join to be valid as well, we just check if everything was processed correctly by the operator, because at this point the operator can do whatever it wants. But here we check if the transfer was actually done as expected. Once that's the case, it's like, okay, everything is valid. Now approve this transfer from the account to the user, and everything is okay. We update the balance inside the Emm account, so we know how to correctly mint tokens in the future. And then at this point, we actually mint the tokens for the user for the amounts that he deposited. So at this point, the minting is quite simple, as in they are not actual tokens, but the minted liquidity tokens are just balances on this contract. So they are automatically locked. For exits, it's the same idea. So well, it's slightly different because at this point, users, it's like if you exit, then it's the Emm pool that needs to authorize transfers from the Emm pool to the user, instead of the user having to authorize transfers to the Emm pool. But it's kind of still the same idea, because the user still has to authorize that he wants to exit the pool under some conditions. So the user still has to authorize this exit by an on-chain transaction or by providing a signature. And then it's mostly the same ID. So the exit is approved now from the Emm pool to the user. If it's on layer 2, if it's on layer 1, if the user requested next on layer 1, then we just update the balances here in this pool, and then the user can withdraw from this pool contract directly, or however you would like to implement it. So one of the things that I forgot to mention is like this approve transaction. This is possible because this is the contract. This contract is the owner of the Amm account on layer 2. So this contract can, by design, just doesn't need any other functionality. This contract can approve transactions for this account because it's the owner. For the joins, it's kind of like still a special case, because now this contract also approves a transaction from the owner of the account. So for this to be possible, we have to use the agent functionality. So the agent needs to approve this Emm pool contract to approve transactions from its account. So that's kind of like another interesting way that all these things come together, with the agents, with the contract approvals of transactions, and like signatures and all that stuff. Okay, let's see how much time is. Okay, time is almost up, but once we've included all these transactions, all the joins, all the exits, then there's still one possibility. So if everybody enters and exits on layer 2, then the total amount of balances inside the rollup remains the same, and we don't have to deposit or withdraw actual funds from or to layer 1. If users deposit and withdraw from or to layer 1, then yeah, the amount of funds available in the account, in the total rollup changes. So we have to actually do deposits to the exchange contract or do withdrawals from the exchange contract. So that's what's done here. So because we just keep track of all the balances in the account and like the expected ones, we know exactly like, okay, this user has deposited 10 ETH on layer 1. Okay, this 10 ETH is still stored in this contract, but now we have to actually deposit this 10 ETH to layer 2 to the Amm account, so it can actually be used for trading by the users on layer 2. So that's one of the things. That's just what's done here. So if we wouldn't support transfers from or to layer 1, then this would be unnecessary. At the end, we still do another Amm update, and that's because there's an additional trick that you can use, so we don't have to. Well, if you have a join, then there's still a signature needed on this pool contract. So we have kind of like this locking mechanism where you are unable to transfer funds to the Amm account on layer 2 if the Amm weight is non-zero. So because of that, we can use these Amm updates as kind of a lock for transfers. So we first disable the weights, so we set them to 0, and at that point we can do transfers to the Amm account. And then once everything is done again, we reset the weights again to their non-zero actual values, and then this disables transfers again and enables trades. So this kind of locks in all the transfers that happen to the Amm account between these operations, which is kind of like a nice thing to have, because let's say the user just signs a transfer like they normally would with their zkRollup public keys. Then if we wouldn't lock it, then we could just use that transfer to do the transfer to the Amm account, but the user wouldn't have any liquidity tokens. So basically the user would have lost all his funds. So by having this locking mechanism where the transfer can only happen between this between these transactions and these transactions, we force the operator to actually do them inside here. And because they are forced to be done between those two, we can also verify them here as well on chain. So that's kind of like another neat trick that we can use to make things more efficient and user-friendly. Okay, I guess that's where I'll leave things. So this quite heavy contract, but yeah. So the goal is, of course, to like do something interesting with it. So either like really do like a balancer Amm pools, or update the weights, like the weights that you can set here in the Amm updates. They are just now fixed token weights. So not much going on there. So you can use oracles, Chainlink to like optimize these token weights in various ways, or yeah, things like that. So if you want to work on it, then I would say like this is where you will spend most of your time to add functionality. You don't have to worry too much about the other stuff like the withdrawing, which is just there for safety. So because users can deposit funds to this Amm account, we also have to make sure that users can get their funds out again in like a censorship-resistant way. And then there's like this test Amm pool test that just is a very simple test. It just uses the Amm pool. Just the user just deposits to it. There's like a single trade on the Amm pool, and then the user gets partly gets his money back out. So it's like a simple test, but I would say like just mainly focus first on getting like the smart contract ready ready, and then if you actually want to test it, you can use this. But yeah, just let me know if there are any problems with getting it running, because I think it won't be that easy to update everything as needed.
Awesome. Well, thank you so much. This was a very informative workshop here. Definitely a heavy subject. Definitely a lot of really interesting pieces going here. But yeah, thank you so much. And with that, we are at time, so we will roll out. Appreciate it.
Thanks.
All right. Bye, everybody.